keep going. See how far we get. And I was looking at the current record, so we have 3 homework problems so far. Is that it? The 1 over 2a spike, the e to the minus alpha x, and then the reverse the Fourier transform. Those 3? I'll add it.
Reversing the transform, there's the a e to the negative alpha value x.
Right.
There's the 1 over 2a spike, and then there's the stuff assigned last week.
It was more from last week. Oh,
It
what was
was
that?
assigned-
I think
it was
we got
assigned
5
last
questions.
week. There was
2 more from last week.
Yeah, there was pi squared minus x squared and the complex Fourier series with the spike starting at pi over 2 and
Oh,
ending at pi.
The one we did in the.
Yes, in resolutions.
That was due this week?
Yeah.
Yeah. Good. Good. Okay, that's that may be enough of this set. We can argue about that later. I have a few more. I'll add at least one more basic thing here. So yeah, we're doing the Fourier integral, the Fourier transform. So here's an interesting one. So actually I'm going to add to that homework list right off that here. And good, we'll just put our formulas up here for the record. So we've got f of x, 1 over root 2 pi, integral f out of k e to the line kx dk. Right? Argument is x, integral over k. Argument's right up there. And then we have this f hat of k, which is just inverts this thing. F of x e to the minus ikx dx. And the nice thing about these, you see exactly where they came from when we did the complex Fourier series, but they have a nice symmetry to them. You have to have functions that we need f of x magnitude dx to be finite. And this would be the complex magnitude because it could be a complex function. So that's a requirement for those things. Okay, that's not the actual homework problem. The homework problem is this f of x equals 1 over 2a for x less than a magnitude, and 0 for x magnitude greater than a. And of course, that is this spike. And it's been constructed so that the area under it is 1. Okay? Because 1 over 2a times the width of this thing, which is 2a, is equal to 1. Okay? So it's been constructed that way. And there's going to be an interesting corollary to this calculation that we do here. And that is that since f of 0 is equal to 1 over 2a, right, we can use the Fourier transform that we find to get 1 over 2a is equal to 1 over root 2 pi minus infinity to plus infinity f hat of k e to the minus I k, we're going to be explicit there, 0 dx, right? So this is going to give us a new integral that we couldn't have calculated by other methods. So I'm kind of giving away the whole thing, but what you want to do is end up showing that just with a generic variable, integral minus infinity to plus infinity, to avoid using x, I'll just say y. sine of y divided by y dy is equal to pi. So that's another thing that we can use. This is analogous to what we did when we summed up those coefficients to get expressions for pi, pi over 2, etc. when we were doing the Fourier series. This is analogous to that. So yeah, I think you'll enjoy that. Once you do this problem here, you got it all under control, it's not hard, and then you get as a bonus an integral of this type. Yeah?
So this is due tomorrow?
Do we have enough for tomorrow?
Pretty sure you gave us that question already.
With this here?
Oh, not now, but
This one I gave you,
Yeah.
yeah. So actually, all you're doing is using this result to get that. Okay.
Okay.
So, yeah, use this, I just wanted to have it up there clearly, right? So basically, use this result to prove this thing here. Yeah, is this for tomorrow or not? Yeah, this is fast. This is fast, because it's really just a corollary to this, an interesting corollary. I wanted to make sure we have that there, because we had been doing those pi over 2 and pi, et cetera, pi squared expressions before. Okay, so there's that. And anything else we do will will be part of next week's homework. Okay, so we're going back to these Fourier integrals. And I'll just keep this up here, because we're going to use this. And there's a handful of interesting relations that allow us to do more difficult calculations. So we're going to have a look at those. They're basic facts about the Fourier series. And under here, I'm also going to put a note. We'll be using this later. But just for the record, right now we're always using this. We've got k, we've got x, and that's fine. But what if you had f of t and you wanted a Fourier integral for f of t? Well, then you could do the same thing. Entire axis. You'd have f hat of omega. Okay. This is important because time series, this would be a frequency e to the I omega t d omega. And then your f hat of omega would be, I mentioned this the other day, I just want to put it up here for the record. We'll be doing this explicitly later on. F of t minus I omega t dt. And of course, if you're talking about position versus time in a mechanics type of problem, you could be doing x of t and x hat of omega, right, by the same token. So we're just using these because they're just letters for us right now. But once you get into time and you have dimensions, then you have to have the inverse of the time, which is going to be the frequency, angular frequency. What if we have dimensions up here, right, which we can very well have, then if that's a length, then that's a wave number, right, inverse length. Okay, so let's get these functional relations that are functional relationships. And I think what I'll do is work some of them and assign some other ones. So we have to write this down one more time. We're going to consider an h of x. Same formulas here. 2 pi h hat of k kx k. Because now we're going to do composites of functions and stuff. So same thing, just another letter. Minus I kx So what we want to do is look at different forms of h of x, okay? Different general forms of this h of x. And the first form is simply linearity. So if h of x equals a f of x plus b g of x, a and b are complex. Okay. Then the question is, and then we're going to do a whole bunch of these now. The question is, if that's your h of x, what's your h hat of k? And to answer that, we literally just go into here, right? This is why I'm bringing into this new function h. We go into this expression here, 1 over root 2 pi, let's see this right away, a f of x plus b g of x e to the minus I kx dx, right? Just by definition. So the linearity of integration means I can do, I can do the sum of these two integrals, and then I can pull out the constant a. So I'm just going to do this, equals a 1 over root 2 pi integral f of x e to the minus I kx plus b g of x e to the minus I kx dx. Just to see how we're doing this. So apparently, this is a, this is f hat of k, this is b, this is g hat of k. So the answer here is a f hat of k plus b g hat of k. So this one's of course very basic, but you can see what we had here. Here's the question. We have a composite function, linear combination, and then its Fourier transform is a times that. So you can do that with more complicated things than just the linear composition. And we have a half a dozen of these interesting little questions. And I'll do a few and I'll assign a couple more, a couple of them as we. Good. What do you guys think? Is this clear what the game is here? So we're going to do different, I'm going to erase this, we're going to do different types of composition and operation on these things. Good. Okay, so I'm going to erase them one by one, I'm going to do them one by one. Let's see which ones we assign. Because a couple of them have interesting induction steps, and we can use our proof by induction that we were doing earlier. So I'll do one more completely. So the second one is if you're just translating a function, along the axis. So here we have, for real x of 0, what we're going to do is let our h of x be f of x minus x of 0. So that's just moving the origin, so to speak, okay? And then the h hat of k, we can just go into that integral, 1 over root 2 pi, integral, plug in the h of x here, so f of x minus x0 e to the minus I kx dx. So this case, got the f of x minus x0. What we're gonna write is the following: e to the minus ik x minus x0. And I then have an e to the minus times minus as well, so I have an e to the ik x0, which is just a constant. Okay, so I have to multiply to make this an equality, e to the minus ik x0 dx. And I'm going to pull that out, so e to the minus ik x0, 1 over root 2 pi. And now I'll do a coordinate transfer. I'll do a change of variables. I'll let y equal x minus x0. So I'll have an f of y e to the minus I k y. And then dx and dy are going to be the same because x not a constant. So I did a change of variables. And you see what's left. I have e minus I k x0 times the Fourier transform, just in terms of k, right? This is just the Fourier transform. The argument is k, out of k. So once you know these, you can do, you can apply them automatically. Especially say if you're in electrical engineering and stuff, you'll learn all kinds of formulas like this and then knock them out consistently. But we're actually more interested in being able to prove everything that we use. So what we have here is h hat of k that I just found underneath there, e to the minus I k x f hat k. Okay, let's see if I make the next one for you guys to do. Yeah, so it's going to be the same program. You guys see it? Can I erase this one? That's some transformation here or some form of our original function, and then we find the form of the Fourier transform. Okay, so number 3. Kind of the inverse of this one. You'd be able to guess it. We'll put this one for the on the homework. So here for 3, suppose h of x is equal to f of x e to the I a x. Find h hat of k. Homework. That will start the ball rolling for next week. You're going to find h hat of k, and again, in terms of the function f, right? In terms of f. Just as we did on number 1 and 2. That's a good one. Yeah. The 4th one, we have room on the 4th one here. H of x. This is just a rescaling. F of a times x. We'll take a as a real number. This one's worth doing. We'll do this one again, and then I'll assign another one. So we're going to do the h hat of k. We're always just going into the definition. We got f of ax e to the minus I kx dx. So this this time we're gonna do a substitution. Let u equal ax, du equal a dx. And let's see what we get here. We got 1 over root 2 pi integral f of u e to the minus I k, and the x is u over a, and the dx is du over a. So when the dust settles, we have 1 over a f hat of k over a. Actually, I've got the u du, so I can have the k over a. So yeah, if you're rescaling your variable like this, then you just automatically get this out there for your Fourier transform. Next two are the interesting ones. I'm gonna let you guys. That works. Okay. Good. Excellent. I think these next two I'm just gonna write down and we'll discuss a bit how to do them. This is all standard material, you know, you can find this all over the place. But so these are used a lot. So the fifth one, h of x is the nth derivative dx to the n of f of x. Then what you're going to find is h hat of k is equal to I k the nth power times the original f hat of k. This is the kind of thing that's used a lot when you're doing differential equations with the Fourier method. And the sixth one is kind of related to this. If h of x is equal to x to the nth power f of x, then the Fourier transform has the form I to the nth power, I'll put parentheses there, I to the nth power, nth derivative with respect to k of f hat of k. So this can be really useful because we've already done, you know, we did the Fourier series, we did an x squared where we saw we had 2 integrations by parts. And here you can replace those integrations by parts by derivatives, which tend to be a little easier. Although it can get pretty hairy too if you have some, a high derivative there. But both of these are proof by induction. And in these cases, they're also true for n equals 0. So you could say n equals 0, and then n goes to n plus 1. And then n plus 1. And you know, you could do n equals 0 and 1, especially doing n equals 1 will kind of show you the strategy here. So these are great.
You want us to do these as homework?
These will be as homework. Yeah, both of these will be homework for next week. And we give a couple tips here. You'll actually find these to be enjoyable. These are tip right here that I wanted to give you. So the hint on the fifth one is you have to use integration by parts. Integration by parts. And if you use integration by parts, you have to throw away the boundary terms. And you can do that and use integral of dnf dx to the n. Minus infinity plus infinity. Less than, well, not so much that one. Here's what you're going to use. Use dn dx to the n of x. Magnitude goes to 0 as magnitude x goes to infinity. So you're looking at functions that have to decrease sufficiently rapidly out to infinity in order to make the proof work. Because if you do integration by parts, boundary terms have to vanish and then you're left with something. So that's for problem 5. And we have for problem 6. Problem 6 doesn't even need an integration by parts. So both of these use the proof by induction. So in that regard, they're very interesting problems. And this one is used all the time once we start doing, and we're going to do this later, once we start doing x of t and x hat of omega, we start doing oscillations and stuff using the Fourier technique. But on the other hand, they're so basic that you can also just implement them on the spot. So these aren't rules that we have to memorize so much as that we just are going to recognize as we go through this stuff. Okay, so there's our discussion of Fourier transforms. I may have a little bit more. I do. We're going to do an application of these, specifically these here. So I guess one of the homework problems for this week, I'll put the answer on the board just to, yeah. Okay, so application here, and an example. Calculated already. So we have this f of x equals e to the minus a, whatever you call it, alpha x. On the homework problem, we had it with what? With some factor in front because we wanted to normalize it as well. But if we don't want to normalize it, let's consider this, and then f hat of k for this one here is equal to 2 over pi root a over a squared plus k squared. So that's the f hat of k. And just to remind you guys, what did this thing look like? It was just equal to 1 right here, and it decays exponentially in both directions. And by the way, in the limit as a goes to 0, this thing gets very narrow, but we'll discuss that later. So suppose now, what if we have, h of x equals x to the n e to the minus ax. And depending on the n, this could be complicated, or just x squared e to the minus ax, what would it look like? multiplying it by x, it's gonna turn it into an odd function. And when x equals 0, it's gonna be 0. So what happens to this function on the right side is it somehow goes up like this and decays, and on the left side, it goes like that and decays. And actually the end would get more and more complicated, but there's an idea of what's going on there. So what does this theorem here tell us about the Fourier transform? Then h hat of k is going to be I to the 1, since I just did n equals 1, it's going to be equal to I, and then d dk of this thing right here. Root 2 over 5, of course, will come out a over a squared plus a squared. And that's not so bad of a derivative, right? We can even do that right here. So we'll have I root 2 over 5 a. And then we've got this 1 over this thing to the negative 1 power. So we have negative 1 a squared plus k squared squared, and then the chain rule gives us 2k in the numerator. And you can see you could mechanically just keep doing the higher derivatives of these, but you wouldn't necessarily want to. I do the first, you do the second, or we put it off for a rainy day. Okay, so that's an application of this sixth one here. So yeah, there are different techniques to evaluate these kinds of integrals, and the ones we're going to be interested in always have some kind of exponential function in them. Or often do. So let's good. Okay, that's going to take us back to the point where we were at the end of the last hour. Just with a little more background. Good. So, can I erase this stuff? So yeah, these are all nice, straightforward, and like I said, I think you'll find these induction proofs interesting. Good. So the end of the last hour, we had this problem that we were doing an integral, and the boundaries of integration were somewhere in the complex plane and not on the real axis. You guys remember that? So that's what we're using as a motivation to extend our integration and differentiation and everything into the complex plane. So we go beyond Euler's formula and just start doing e to the z, for instance, and things of that nature. Let's erase this forward. In fact, that's going to give us, we'll spend several days on it, that'll give us techniques with which we can return to these complex integrals and do even more. Return to these Fourier transforms and do even more. So yeah, to get the full benefit of these techniques, we have to go into the complex plane. And that's the next topic. Okay, so this next topic, complex analysis, it's referred to as, also referred to as theory of functions. Functions of a complex variable, but sometimes it's called theory of functions. And the motivator was, we had this integral from minus infinity to plus infinity. I'm just going to draw it that way. Except our boundaries of integration were from this point to this point. Okay, this was the x-axis, this is y. And what we did, we just did a substitution and knocked it out and acted as though it were just the real axis. And that's what you're going to do on that homework problem again when you reverse the Fourier transform. Okay. But because of this, you know, the path from here to here, what I was saying was it was actually going to be this path, and these two branches were going to be utterly negligible because we're going to drop to infinity. So that's the answer why everything we do works out right. But we do have to learn about integrals in there. Not just integrals, functions in general. So this was from last time, that path integration. Now let me consult my concept here. Let's see what we can do. Somewhere here, yes. Yeah, so we've done all this preparatory stuff. We're comfortable with complex numbers. So we're going to do functions of a complex variable. And spread this off. So we'll just say we have a W equals f of z, right? So the argument's complex, the function's complex. Examples. F of z equals z, f of z equals z squared, etc. That's a function. F of z equals z star. That would be a function. So, you know, you'd have f of x plus iy is equal to x minus iy, right? That's a fine function. You could have multi-valued functions. So, f of z equals z to the 1/2. So you have, you know, square roots, you have two values of f. And for multi-valued functions, we'll have what's called a branch cut. Although we're not going to do much with that. So for multi-valued functions, you can define what's called a branch cut. For example, this one. And then when you're doing integration in the complex plane, you agree to never cross the branch cut. Okay. Branch cut. I'll just have that up here as a piece of terminology right now. So the next way we can look at that is mappings, and W equals f of z equals u plus I times v. So when we write a function in this form, we're talking about a real part and an imaginary part. So we have f of x plus iy is equal to u of x and y plus v of x and y. So then we have a real part and an imaginary part of a function. So u of x and y, and am I gonna call that w here? Yeah. So u of x and y is the real part of w, and v of x and y is the imaginary part. So that's terminology, but actually it's more than just terminology. Because now we get to the derivative of these functions. And the beauty is we just start with our standard definition of the derivative. Okay, so leave this up here. Okay, so derivatives, we go like this. So f prime of z is going to be the limit f of z plus delta z, I'll write it this way, minus f of z divided by delta z, as delta z goes to 0. This is actually just the same definition, but you know, when I introduced the derivative earlier this semester, I had done this, f prime of x equals f of x, or, sorry, I had done this, I had done limit x goes to x naught, f of x naught, x minus x naught. And I did it that form because I wanted the point slope formula as the approximation. But we could also say f prime of x equals limit delta x goes to 0, x plus delta x. Delta x. Are these two equivalent? That's the question. Should have done this earlier. They are equivalent. Okay. I'm just relabeling. Right? I'm letting my delta x be the x minus x naught. So in this form, these are equivalent forms. In this form, you know, I'm taking the limit as x goes to x naught. Here I'm saying, you know, x plus delta x is what the x was up here. You guys familiar with both of these? Hopefully. So anyway, this is the one we're using here, but they could both be, you know, they could be used interchangeably. You could also use this definition up here in the complex functions. Okay? They're totally equivalent. And the important thing is this is possible. So this was real down here, real. This is well defined and possible because all of the algebraic properties are present with the complex numbers. But what we're going to see is this is much more demanding of a function in order for a function to be differentiable, even though all the same rules are going to apply. The reason being is we have to be able to approach delta z goes to 0 from any direction. So important here, delta z goes to 0 from any direction. and you wanna take a derivative out here at some point z. In the world of real numbers, you always had to approach from left to right, or both, right? From the left and from the right. In the world of complex numbers, you have to be able to approach it from anywhere. Your delta z has to be able to converge to zero. So you approach z from any direction. And that will have some interesting consequences. So what we're going to do is set this up the following. So consider the derivative, we'll just put it in kind of simple form. df dz. Consider this limit. Consider limit as delta z goes to zero. Okay. And we're going to use that form that I just erased. So we're talking about the limit delta z goes to zero, du plus I dt over dx plus I dy. So this is the differential of the function, and this is the differential of the argument here. Now equals limit delta z goes to zero. But we're going to do it where delta, which one am I doing first? Do it where delta x is equal to zero. So if delta x is equal to zero, I'm approaching it along the y direction. Because I can approach it from any direction. Okay, so the delta x is equal to zero, so I'll just rewrite this. du plus I del v over I del y. And we're going to end up with a 1 over I du dy plus dv dy. And just to be concrete about it, we'll multiply top and bottom by I. We'll have minus du dy. I'm sorry, minus I. Top and bottom by I, minus I du dy plus dv dy. So that's the derivative taken along the y direction. I'm going to go along the x direction. Similarly, we're going to do df dz equals du plus I dy dx plus I dv dx plus I dy. So now we're going to do it where dy is equal to zero. So I'm just doing the same thing I did here over here. So if the dy is equal to zero, I have du over dx from this quotient and plus I dv dx. So the upshot is, here we go. We took this limit here, so this is the derivative. This is our f prime. This one here turns into our f prime. And we want these two results to be equal to each other. Use the bottom of the board right here. We want these two to be equal, so let's just go ahead and write them out. So we need du dx plus I dv dx has to be equal to minus I quality of these two, because this, real and imaginary parts, complex number, real imaginary parts have to be the same. So what we have to end up with is requiring the du dx be equal to dv dy equals dv dy, and dv dx equals minus du dy. Dx equals minus du dy. So you see, you can't have just any old functional relations and have differentiability. And these are called the Cauchy-Riemann. Riemann equations. So yeah, differentiability requires more of a function in the complex plane than it does on the real axis. I'm going to give some examples of these now. This is just formal, but these results are pretty useful. So for one thing, as far as differentiating goes, though, we're just using the same rules we ever learned. Okay? It's just a question of whether a function is differentiable. So yeah, we'll just finish up with some general viewpoints here. So the example is f of z equals z star differentiable. Question mark. Is that a differentiable function? In other words, what we're saying, i.e., we have f of x plus iy is equal to x minus iy. So u of x and y x, v of x and y is equal to minus y. That's the function, just complex conjugation. We go back over here, we have du dx, which is 1, is equal to dv dy, which is minus 1. What world is 1 equal to minus 1?
In some really weird vector space where it somehow makes sense.
Exactly.
Absolute value.
Okay. So this already fails the test, right? Fails the test, so it's not a differentiable function. What we're going to learn later is that if a function is the complex plane of is differentiable once, it's differentiable infinite number of times. That goes far beyond real functions. So let me give an example of that. So the answer, note, fails Cauchy-Riemann because du dx is equal to 1, dv dy is equal to minus 1. Okay. So differentiability. On the other hand, these x squared, x cubed, x to the n, they're all differentiable. And the derivatives are exactly what we're used to. But I'll just give some examples of differentiability in real versus complex. So just as a note, we will find eventually that if f prime of z exists, then the nth derivative of z exists. all n. So one derivative implies infinite number of derivatives. Can you guys give a counterexample in real functions where one derivative existing doesn't imply infinite? Infinite differentiation. Continuous infinite, derivative has to be continuous too, right? They exist, many of these exist if you do some constructions. Okay, you can't just write the function down necessarily. After all, the absolute value, you can't say a derivative exists, right? Because it's plus and minus. But say you have a function here equals 0, identically equal to 0 for x less than 0, and then just let it equal to x squared for x greater than or equal to 0. That's a smooth function on the real axis. Okay? The derivative here is always 0, then the derivative, the first derivative, f plus is the plus side, prime of x is equal to 2x. Okay, so that works, but f double prime is equal to 2. Okay, it's no longer a smooth function. And after that, the third derivative. So that's not although this is smooth here by construction, and if you had x to the 4, 5, 6, it would be smoother, but eventually it's not smooth. Okay. On the other hand, a complex function is going to be, the derivatives are going to exist all the way to n equals infinity. We can't prove that yet, but it's interesting. Once we get some theorems about the first derivative, and then we're actually going to be able to construct the Taylor series and prove that we get infinite differentiability. So that's what's going to happen here. Let me see if I have any. I have a couple more definitions, if anything. Yeah, I'll just get us a couple definitions here, and we'll start doing integration next time. So definitions, this is sort of how to talk about these things. Restricted set of theory of functions, but we gotta hit the important ones. Okay, so let's call this definitions. And the first one here, if f is differentiable at x0, about z sub 0, then we say f is analytic. Analytic means differentiable and z sub 0 is what we call a regular point. Like I just said, eventually analytic is going to mean infinitely differentiable. Right now it means differentiable once. So if f is not differentiable about z0, then we call z0 a singular point. F not differentiable about z sub 0, then z sub 0 is a singular point. And the third thing, if f is differentiable everywhere in the complex plane, then it's an entire function. Differentiable everywhere the examples for this, just your polynomials. Polynomials are just utterly well behaved. Example here, f of z equals e to the z sum over z to the k over k factorial, right? That's an entire function. It's completely well behaved. It does everything the exponential does that we're already familiar with. Something that wouldn't be an entire function, but still well behaved, would be if you have a z minus z sub naught to the k. So let's say you have an infinite series of this form here. This could be differentiable within a radius of convergence. Because we talked about radius, convergence of these things, and you're going to have a convergence criterion. So I'll just write here differentiable within a radius of convergence. Convergence. Okay. So yeah, very fortunately, the polynomials, exponentials, those functions completely well behaved, and we're going to be able to do, they're well behaved in this sense too, completely differentiable. You're going to be able to do a bunch of interesting calculus with them. So what we'll do next time, a little more with these functions here.